Okay, welcome everyone. Today we are going to look at section 3.2. Now, as we have moved through this first unit, everything has seemed like there's been a lot of new topics and concepts for us to struggle with. But this section, we're really going to be doing a lot of review and a reminder of things that we have already worked on. So hopefully a lot of this is going to be review. Now remember, you have control of this video, so I want to encourage you to go ahead and pause it right now. I want you to go through and look at all of these parent functions and see if you can name them. Tell me what type of function they are and what the equation would be. For example, this first one is what we call the constant function. It's linear, but it's a specific linear function. It's our constant function because it has a slope of 0, m equals 0, and the equation for this function is going to be y equals some constant c. Now this particular function, I can't read my numbers because they're too small, but let's say that that's a 2. This would be y equals 2 for this particular function. But any constant function is going to be y equals a constant. Alright, so take a minute, go through, name, and give the information that you know about each of these parent functions, these most basic of functions. Hopefully you got that this was a linear function. The parent function, the equation is y equals x. Here's my absolute value function, and I know it's an absolute value because it is a V shape. The equation for the parent absolute value, y equals absolute value of x. Then this is the one we work with a lot, right? Our quadratic function. It's our squared second degree function, y equals x squared. Anytime we see that parabola, it's always going to be x squared. Something to note, these functions I copy from the book don't have arrows on the end, but I want to encourage you to be sure that as you do your work that you show me where these graphs continue by placing arrows on the ends of your functions to emphasize that, for example, I know for my cube root function down here it continues in both directions. This square root function, however, just continues in one direction. So I want to encourage you to put arrows on the ends of your functions. This is my cubic function, y equals x cubed. I just mentioned that this was square root. We think about that being my parabola, flipped across that line y equals x, turned on its side, but we're just interested in the top half to make it a function. So we're just interested in the positive values, square root x. And then finally my cube root function, y equals cube root of x. If you can remember all of those basic shapes, it's going to make things a lot easier as we focus on transformation of functions. Okay, application of interpreting these graphs. Now this particular graph shows iPhone sales in millions of units, so when I'm looking at these numbers, that's for example 50 million, 100 million, etc. And then the years that I'm going through are over here. Function value is how I refer to my y value. Y is the same thing as f of x. So my function value for f of 2013 is asking for this x value, what is the value of the function or the y value? So if I go over here to my graph, 2013, I go up and I see that that is 150 million phones. 150 million iPhones. And it's sales, so have been sold. 150 million iPhones sold in the year 2013. What is the domain shown? Well, the domain is my set of x values, so I'm reading along the x-axis, and we have individual values, so discrete values, not continuous values, from 5 years. So I've got the years 2011 to 2015. They're included. We have values for 2011 and 2015, so I use my square brackets for my domain. The range shown in the graph, well, my values on my y-axis start at 0 and go up to 250, but the specific range of the values that I'm shown starts let's say that's at 75 million. And probably up to, that's 200, 250. We'll say 225. And that's in millions. Again, my values are inclusive because these endpoints are filled in. Those are values that we know. Okay, let's move on to reviewing how we graph linear functions. To graph a linear function, you have to know the slope. The slope is how we refer to the steepness of the line. If it's positive or negative, is going to determine if it's an increasing or decreasing function. But in general, my slope we have defined as change of y over change in x. We've also talked about it as rise over run. Specifically, the formula for slope that you're most familiar with is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. We have to know the slope to do either of my equations for a line. Alright, so my slope-intercept form we solve for y equals mx plus b. That order matters. We want that x term first, the intercept, the constant last. M here is my slope. And the constant b, if x is 0, then b is the value of my y-intercept. So that is my y-intercept, 0, and then whatever value b is here in my slope-intercept form. We like the slope-intercept form best. That's the form that's most useful to us in graphing our line. So a lot of the time that's what I will ask you to put equations for a line in, is the slope-intercept form. I can only start with a slope-intercept form if I know both of these pieces of information, the slope and the y-intercept. If I don't have the y-intercept, if I just have some random point, I'm going to use the point-slope form because the point-slope form works with any point on the line. My point-slope form is y minus y sub 1 equals m times the quantity x minus x sub 1, where y sub 1, x sub 1, that's the point that I know. That's what I'm filling in. I'm going to fill in my slope, and I'm going to fill in that random point that's on the line that's not my intercept. Alright, let's graph a couple of lines using our slope-intercept form. Now, these are both linear functions, and I know that because it's just in terms of x. It's not x squared, x cubed, absolute value, anything like that. It's just x. So I know some stuff based on the form my line is in. It's slope-intercept form because it's solved for y. This is my slope. My slope is positive, so my line is going to be increasing. And this is the value of my y-intercept. So it's going to start on the y-axis at the point 0, 1. That's my starting place for graphing my line. Now from this starting place, this point where I can start on the y-axis, I'm going to apply my slope, go up and over. Now I want my line to be increasing. The slope is positive, so when I go up and over, I'm going to go up to over 3. That's a point on the line. Or I could have gone down to over 3 in the other direction. That's also going to give me a point on the line. I only need 2 points to draw a straight line. So I'm going to connect those points, make sure I put my arrows on the end to show that that line continues. But the other thing that I was asked to do, always make sure you read all of the instructions. I'm asked to identify the domain and range of each of these lines. Now, unless it's a constant function, a horizontal line, or a vertical line, which is not a function, my domain and range of my linear equations, my linear functions, is going to be all real numbers, negative infinity to positive infinity. I'm sorry, I messed up the infinity sign again. Let me see if I can make that a little bit neater. Negative infinity to positive infinity. So given that information, I know that when I graph this line over here, my domain and range is still going to be negative infinity to positive infinity. Anytime it's all real numbers, it stays all real numbers. There's no transformations I can perform that's going to make it not be all real numbers. Okay, as I evaluate this equation, I see that I have a negative slope. My slope here is a negative 3/4. Notice I don't write down the x when I write down the slope. My y-intercept is a negative 2, so my y-intercept is 0, negative 2. That's my starting point. On the y-axis, I start at negative 2. I have a negative slope, so my line is decreasing. It's going to start high and finish low. As I move across the x-axis from left to right, my line is going to go down. So I need to keep that in mind as I apply my slope. I can either go up 3 and to the left 4, or I can go down 3 and to the right 4. So I would get a point here. This point would be at 4, -5. This point was at 0, -2. And I only need 2 points to make a line. So I'm going to go ahead and connect those 2 points. Just over here, my coordinates were 0, 1. And then when I came over to 1, 2, 3, 1, 2, 3. So I was at the point 3, 3 here. All right. So that's graphing two linear functions. Let's look at the next page. Now for number 3, sorry, it took a second to focus. For number 3, I can't just start graphing using slope-intercept. I could find my x and y intercepts and graph using those. I could plug in 0 for x, plug in 0 for y. That one's going to be a little ugly. That's not going to be a whole number. So graphing using my x and y intercepts is going to be a little bit of work. Let's go ahead and let's just solve this for y and put it in slope-intercept form. To solve for y, I need to move that x term over. That leaves me with -2y equals -8x minus 10. Notice I put the x term in front of the constant. And then I need to divide out that coefficient. So everything gets divided by a -2. Every single term, all 3 terms. Anything over itself is just 1, so that's 1y, which is just y. I've solved for y. -8 divided by -2 is a positive 4x. -10 divided by -2 is a positive 5. So that's this line in slope-intercept form. So I have a very steep slope. My line is going to have a steep positive slope, 4 or 4 over 1 for my slope. And then my y-intercept, where x is 0, y is a positive 5. So my starting point is at 1, 2, 3, 4, 5, and I need to go up 4 over 1 or down 4 over to the left 1. That works as well. 1, 2, 3, 4 over 1. That point would be at -1, 1. This point is at 0, 5. And I connect those 2 points to form my line.